Thank you very much for the introduction, and it's my great pleasure to give a talk here. Thank you very much also to IPAM and, for the invitation. So I would like to talk today about some data assimilation problems, not necessarily related fully on traffic. So I've done some traffic state estimation also in the past, but I'm also interested these days in generally over in data assimilation. We have switched a little bit to robotics, so it's still part of autonomy automation, but for a different application. So the topic that I would like to discuss today is flash flood monitoring and the use of robots in the form of unmanned aerial vehicles to perform the sensing and the monitoring. So the main motivation comes from, I hope that all of you can see my screen, by the way. So here. So the main motivation is flash flooding. So flash flooding is a major issue, similarly to traffic. It's one of the most common natural disasters worldwide. So there are significant issues that are similar again to traffic in the sense that we need to sense and we need to perform control. So the sensing part is very difficult because it's very costly. You have some very large geographical areas. This is an example of a watershed near Jeddah in Saudi Arabia. So you can see the very wide areas that can be flooded. So it's really actually hundreds of or tens of thousands of square kilometers, and it's very difficult to flood these things. To sense these things. In particular, it's very difficult to have sensors that work and that are cheap enough to be deployed on these huge areas. Satellites don't work, unfortunately, because they don't work in real time and they are not always over some area. They are low orbiting satellites, so they stay a very short amount of time over a certain location. The fixed sensor networks, they are very costly, as I mentioned. The floods are very fast dynamic events that occur over minutes to hours. They occur on very large scales. The behavior is highly nonlinear, similarly to traffic, where we have a breakdown and the apparition of instabilities and congestion. And we also have, similarly to traffic, very high model parameter uncertainty. So in traffic, the parameters, for example, the free flow speed, the congestion speed, and the maximum density, the critical densities, all these things are a little bit uncertain, but here we have also this uncertainty that is distributed over space. So we have, for example, Manning coefficients to describe the uncertainty associated with the flows of water. And we have also the elevations that are not precisely certain. So there are a bunch of the runoff coefficients also that tell you the fraction of water that gets absorbed by the soil and the fraction that runs off. All these things are very uncertain. And in cities, we have a constant evolution of cities that keep changing over time. So you cannot, for example, use the past flooding results to predict the next flood based on that. So here, there is a need, obviously, to do some sensing, and what we are investigating is the use of UAVs for performing this sensing. So my talk will be focusing initially on just the technical side of using UAVs, so just to give a perspective of what we can do and the numbers of problems that are left, because really this is a very complicated problem that goes well beyond control, obviously. We'll just discuss one of the specific aspects today, which is the specific problem of path planning of UAVs. So the high-level control of UAVs, how do you perform the allocation of sensors and how do you move them across your geographical area to maximize the information that you gain, or to minimize the uncertainty over a certain time. So here, let's discuss a little bit on the technical aspects of these things. So we have developed in the past, in my research group, some fixed flood sensors that could be used in cities. And this is an example of what we had designed with ultrasonic rangefinder, passive infrared sensor arrays, plus customized printed circuit boards. So wireless sensor networks are of course something that is very widely used in smart cities, but there is still some difficulty when using them for floods. So one of the difficulties really the cost. It's very expensive over some large geographical areas. We have deployed some of these sensors for testing, and we have detected actually some flash floods. We tested for 2 years, and we have seen, I believe, 3 flash floods over the time. So they were at different locations, obviously, because floods are very infrequent. But it's still very expensive to deploy, especially when it's very large. And there might be other situations, of course. So in rivers now it's a little bit less expensive, and actually a lot of rivers are instrumented with radars to measure their water levels. But that's the main difficulty associated with fixed sensing. So you can go with mobile sensing, and for mobile sensing there is always the remote sensing that is based on satellites. So satellites are very commonly used for flooding, but they are not used for real-time monitoring. They are more used to estimate the a posteriori damage by taking, for example, some pictures. One of the biggest issue of satellites is that you can't steer a satellite to go over a certain area with a short notice, obviously, and they are just flying certain orbits. So if you're lucky, you could see something. Unfortunately, during floods also, it's very hard to see something from a satellite, I should add, because even if you are lucky to be right above the spot where the flood occurs, the instruments usually don't go through the cloud layer. For example, you cannot use cameras, obviously, because you have lots of clouds. You cannot use also synthetic aperture radars. So these are radars that can give you the elevation of the ground. So you could use them theoretically to estimate if there is water on the ground and if there are flows, but the reality is that these radars are still too uncertain. So they have an uncertainty of about 20 centimeters in height. So that means that you can never be sure that a flood occurs. So it's actually, a flood is dangerous above 10 or 20 centimeters of fast running water. You already have a risk of dying in a flood. So it's something that doesn't need to be a major, to be dangerous. So what we thought instead was to use unmanned aerial vehicles that could throw some disposable pingers on some geographic area. So we would need to fly, obviously, during this bad weather, throw these pingers and get some information from them. So they would be as cheap as possible, of course, to be destroyed and operate only for a few hours. And we would send the information back, of course, to a ground control station. The ground control station would then steer the UAVs to tell them to sense specific locations. So this is a little bit the complexity of the prime, because you have mobile sensors. It's a blessing, obviously, because you can cover very large areas, but it's also a curse computationally, because you have to determine how to best allocate your UAVs to fly over some areas. So how can you maximize the information that you gain by exploiting the information that you have, plus the added information that you keep getting from your sensors, and what should be the optimal strategies there. So that's what we're going to focus on today. On the technical side, we have also worked on the problem of making flood sensors. So these are the tiny sensors that we had designed with one of my colleagues at cost. So this is a sensor that is made on a printed circuit on paper, so it's very cheap to make. The novelty here is that the antenna is actually printed on the packaging of the sensor, which is paper. So everything is paper except the chip inside, and of course a small battery. So that could be extremely inexpensive to produce, and obviously that could be quite useful for these applications, for these very short lifetime sensing applications. There is also another huge difficulty, which is the problem of low-level UAV control. So when you have floods, how do you fly UAVs in very bad weather? That's really the difficulty. I mean, theoretically, you could fly UAVs in bad weather, but in practice, you know that they have 100% chance of crashing. Even in good weather, it's actually challenging to fly UAVs. So this is an example of UAV that we flew in my group a few years ago. These UAVs have complex dynamics, and so this is the differential, the ODE that describes the motion of the UAV. So it's a 12-dimensional system. And the problem is, how can we equip these UAVs with flight envelope protection systems, a little bit the same as what we have on commercial airplanes, to prevent pilot errors, or here in this case to prevent autopilot errors. The autopilots actually are very simple and crude systems. They only regulate altitude, speed, and other parameters, but they are completely unable to get out of a stall or to get out of a spin or to recognize an over-G situation like a pilot would. So it's really something that, I mean, it's adding intelligence to the UAV, and that's a challenging problem. It's not as challenging, obviously, as autonomous vehicles because we don't have the coordination issue, but the high dimensionality issue is a challenge still because we cannot use classical control methods. So here, the idea that we have explored was to design some algorithm based on machine learning to essentially try to predict over a certain time horizon what will be the evolution of the UAV. So we can use classical ordinary differential equation solvers to compute the evolution of a certain system. What we do is that we train, we then recognize from these initial states. So as a function of the initial state of the UAV, we know that there are a bunch of outcomes that can happen when you manipulate all the controls of the UAVs. And what we want is to determine what is the safe set of inputs that can exist based on the initial conditions. So if you give me an initial condition, to what extent can I manipulate the controls of the UAV over a certain time horizon to ensure that over a larger time horizon, the UAV doesn't overspeed, over-G, stalls, or hit the ground and other issues. So this is again difficult because it's a 12-dimensional system, so we cannot solve that in real time. We have to use some offline computations. And our idea was to use an ellipsoidal approximation of the safe input sequences. So we have possible inputs that can be applied on the UAV. So there are 4 controls: ailerons, elevator, rudder, and throttle. But if you take a certain number of time steps, you have, of course, you're multiplying that by the number of time steps. These are your possible sets of actions. That's the dimensionality of your input sequence space. And what we determine is an ellipsoidal approximation, of what are the safe inputs sequences that we can have in this space. And that works quite well because we can have efficient approximation of sets in high dimensional vector spaces through ellipsoids, even though we have also determined in that paper that in some situations the ellipsoid approximation could fail because the safe input sequence set was actually disconnected, it was disjoint. But I think it's still a reasonable approximation for the start. So we have tested that on an actual UAV that we implemented and tested on an Austin airfield. And here, this is an example of situation in which we try to stall the UAV. So you have here the projection of here we are just taking a manifold of this input sequence space and the corresponding ellipsoid cuts. And here we try to stall the UAV. So you can see the blue command here correspond to the actual input of the pilot on the elevator to try to stall the UAV. And the red input is the actual command that is sent to the elevator of the UAV. So we have a system that takes the input of the pilot and that then projects the input onto some safe sets in real time. So we implemented that, and that required to run an autopilot plus an Odroid computer. So the autopilot, the PixHawk autopilot plus the Odroid computer together at the same time to perform this operation. That run at 50 hertz. So this is again just the technical side. Now what we want to do is to do the high-level control of the UAV. So the high-level control of the UAV, so assuming that we can have the technology, the sensors, and the UAV that can fly in bad weather. Now what should we do in order to maximize the information that we gain over some time? So this is really the challenge here. We have a flood. So this is an example of elevation map of Austin. So we have a flood that's supposed to occur. We want to maximize the information. So very quickly, over 10 minutes, for example, we want to have the highest precision map of the current situation so that emergency services and others can help the population decide evacuations, and so on and so forth. So how do we optimally steer the UAVs to maximize that information? So assuming that we have the UAVs and the sensors that are available, how do we do that? These are the challenges that we have to face. First, we have some uncertain prior. So the state of the system initially is not well known. So it's a bit the same as in traffic. When you have an accident, you still don't know exactly before the accident what is the state of the highway. We have uncertain model parameters, obviously, and the model parameters are also very difficult to estimate because they are changing over time. So, for example, the Manning coefficient map that you had for the city of Austin has changed over time because now we have new expansions, we have new sewer systems, we have new buildings, etc. So everything keeps changing. We have uncertain future rain rates. So these are the inputs of the model. They are also uncertain. So you don't know when the water is going to come from the sky and at what rates, and where also, the clouds are going to appear and form. The system is highly nonlinear, obviously. And you can see the transition very, very quickly. So when you have a flood, for example, you have a lot of high rain in some area, and then suddenly the soil cannot absorb the water anymore. So it starts to run off and the rivers form, and everything is highly nonlinear. It's very, it's evolving very rapidly, and the information is needed very quickly. So we need to have the information as fast as possible in this kind of situations. So now I'm going to discuss that problem a bit more in detail, the problem of UAV path planning. So how can we perform this high-level control? So for this, I just would like to give a little bit of background on what we are doing typically when we have a problem of mobile agents that need to sense a certain area. And the key idea first is to start with the basic estimation data assimilation algorithms. So for example, here I'm showing the ensemble Kalman filter. So if we have a certain state here for the system, so BS would correspond to the state of the geographical area. So it would correspond to the distributed values of the water levels and the speeds in the area that you want to monitor. So that system evolves according to a certain evolution equation. So you have a certain dynamics, and we can perform the estimation through measurements. So if you obtain measurements of the state at different locations, you can run a Kalman filter that will have a prediction step in which we will predict the future state of the system according to the dynamics of the model and the forecasted inputs of the model. So how much rain is going to fall, and we have an update step. So this is the update step. So how do we update the state? So we take the prior estimated states and we add to this information so it's a classical thing. So you take the matrix that correspond to the observation matrix, and you multiply that to the difference between the measurements that you're getting minus the predicted measurements that you are supposed to get. That's the innovation part. And of course, the gain, the multiplication of that, that's the Kalman gain. That depends on your uncertainty and how you configure your uncertainty for your what is the covariance of your state essentially, and what is the measurement covariance. So what's the covariance of your sensor measurements? So that's the estimation data assimilation step. So this is the classical Kalman filter formation. So here now, how do we quantify the information that we gain from measurements? There are many ways to do that. So we did some literature survey, and we found that there are various ways of representing what information you get from some distribution based on some prior distribution. So you can use the KL divergence, alpha divergence, for example, here, or you can more use the log determinant of the covariance of the state of your system. That's also a possible way of evaluating the uncertainty on your system. And what we want ultimately is to either maximize the information that we gain in a sense. So with these heuristics, we have some qualitative way of measuring how much information we gain from a system, or minimize the uncertainty on the system. And so minimize the covariance matrix essentially. That's what we'll try to achieve. And we have some models that will be models of the system. So here the BS, this has some dynamics. So in this dynamics, the classical dynamics of these floods is given by a flood propagation model, so the shallow water equations. But what we are doing instead is that we're going to use some data-driven models. So we're going to use some approximation of the shallow water equations. And there is actually quite a bit of literature these days about replacing partial differential equations by deep learning approximations of partial differential equations. So it's not really perfect. I mean, you still have considerable differences between the actual PDE and the deep learning approximation of the PDE, but you also have a lot of reduction in computational time when you take a deep learning approximation. So it's really a trade-off, and it can be quite considerable here. So. Here, the problem that we want to describe will be summarized in this formula. So this is the formulation of the optimization problem. Omegas are the actions here. So we have a certain action set. We have a bunch of UAVs that are at different locations. And what we want is to decide independently what each UAV is going to do in the future. So what we try is to minimize the accumulated uncertainty over some time. So we have some reward function that correspond to the uncertainty that we are getting at the end. So here it's something that you can compute based on the, for example, the divergences that I showed before, or the log determinant of the covariance matrix. We have also, of course, a discount factor gamma to just ensure that the information that you get, I mean, the sooner you get the information, the more important it is. Then we have some constraints associated with the dynamics of the system. And so here, this is the objective, but the constraints are the dynamics. So here, this is the fact that the water follows the Saint-Venant or shallow water equations. We have some observations that come from sensors with some observation matrix. So the observation matrix is not known in advance, obviously, because that's what we try to determine. The observation matrix will correspond to where you are at which location you are when you perform the sensing. Then we have some data assimilation constraints. So this data assimilation constraint is something that I would say is the key part in the difficulty of the problem. So if we had just these constraints, that wouldn't be too complicated, because the only difficulty would be how to choose this observation matrix. So basically how to choose the position of every UAV over time to minimize that accumulated uncertainty, given the dynamics that we follow a flood. And of course, there would be also another constraint here that I didn't mention, the action constraints. We have to follow the dynamics of the UAV. So the UAVs cannot teleport at some location over time. So we have a certain reachable set here given the performance of the UAV. And the reachable set might be something complex to get because you are affected by winds, for example, and the winds can be time varying. So we have to take that into account. But for now, the most complicated part is the data assimilation part. So the data assimilation part means that whenever you're going to perform your optimization over your time horizon, capital T, you will have to take into account as well the added information, the transient added information. So you're scheduling the positions of the UAVs over time, but you know that after one time step, the UAVs will have obtained information. You will have rerun a whole data assimilation cycle based on this new information. And based on this new information, now that will affect, of course, the decision that you will have next, because you can find out, for example, that you expected water and there is no water there. So that tells you that you're in some other situation, and that's, of course, some information gain. And here, this makes the problem very complex, because you don't know how to, in advance, you will modify the state of the system, given that you don't know what you're going to measure. So it's what you're measuring at this point is unknown when you're starting the problem. So that's, I would say, the complexity. So for the constraints of the dynamics, they followed. So here we took the shallow water equation, so the SWE, which are just the classical equations, the Navier-Stokes equation applied to shallow water flows. We have three state variables that are the height, the water, and the water velocities, and the two water velocity components. over 2 dimensions, and we have some inputs. So the inputs are the precipitation, so how much water is flowing from the sky, and also the flows from the boundaries. So if you have rivers, you have also some estimated flows that you have to feed in the model. And the parameters are distributed over space. So we have the topology, what is the map of elevation, and what are the friction coefficients in the sense. So the elevation, I also forgot the runoff coefficients as well, but here the runoff coefficient is more something that we can put within the inputs, but the 3 key parameters are what are the elevation of everything over space, what are the friction coefficients, so how much friction is there on the ground, because that affects the flows, obviously, and also the runoff coefficient, given some forcing, given some precipitations, what will be the actual flows that will remain on the surface, and what will be the flow that will be absorbed. And that's also something that varies over time. So the data assimilation step, this is the major bottleneck, as I mentioned. So what we do for this assimilation is that we replace the shallow water equation model by a deep learning based model to predict the state over the horizon that we want to. So this is how it works. And what we did is offline, we made a simulator, a flood simulator based on the shallow water equation. So we programmed the shallow water equation solver. Then we performed a zillion simulations, and we learned the relationship between the inputs, the initial condition inputs and the outputs. So that means the state of the system at a certain time horizon. And we replace that thing. So that function that is based on deep learning, we replace that. We replace the shallow water equation with that function, and that's actually much faster. There is a considerable reduction in computational time. I forgot exactly the amount, but it was really very large. It was really on the order of hundreds or thousands in terms of reduction. So it's actually also relatively accurate. But these are the targets. So these are the predictions from the shallow water equation on top that you can see. And so we have used various neural network models to try to represent what happened in this partial differential equation. We have also changed changed the amount of noise that we added to the training to make it more robust. We have tried also generative adversarial models, but they didn't seem to work better than the classical convolutional neural networks. So we kept convolutional neural networks. And you can see that there is not too much difference. I mean, there are some differences, obviously, in some of the regions, because there is some accumulation here. You can see that is a little bit different, but you really have to squint to see on these maps the difference. So it's not really very large. It's something that can be used reasonably to predict the evolution of the flood over some time, very fast. We have also the action constraints, as I mentioned. So the action constraints are the constraints on the UAV itself. So what should be the reachable set of the UAV, and this is where it's much easier than in classical transportation systems, because we don't have when we fly, we can fly in direct line of sight to any location. We just have to take into account the wind and the flight performance of the UAV. So now the biggest difficulty is to try to have a tractable way of solving this optimization problem. So if you look at the original system, so here we take a very simple example of a system with a finite number of states. The difficulty of this search is that you have to look at, you're searching over the set of actions of the UAVs. And if you look at the set of actions of the UAVs, so you have to start with a prior. You have to perform some action. So when you perform some action, you're obtaining some measurements. Then with these measurements, you're performing some data assimilation step, which allows you to get a new prior, and then you repeat the cycle. And of course, it's going to be an ever expanding tree that will expand extremely fast, because the possibilities grow. I mean, of course, in all trees, they grow exponentially, but here the rate is extremely high. So this is something that we cannot solve in real time, even for extremely small systems. It's almost impossible to solve. So what we are doing instead is that, so the bottleneck here is really the data assimilation step, because whenever you get a new measurement, you're possibly getting a new state of the system based on this new information. So you have to somehow incorporate this new information. So what we did is that we replaced the data assimilation step in the search by some function of the current state covariance. So we use an empirical function that allowed us to estimate what would be the information gain, essentially empirically, instead of doing the entire assimilation step that would give us the actual information gain, because at the end of the Kalman filter step, we would get a new covariance matrix and we could compute, for example, the log determinant. So this is impossible to do because that takes too much time, but instead we take just an empirical function here. So that's where the heuristics kick in to perform this search faster. And so this is the approximate formulation now of this path-spying problem. So now instead of having this R function that was defined before, so we have now this gamma function that is some approximation of the information gain, and we are going to compound this information over time. So this information gain over time, but these information gains are going to be empirically computed. So we take a certain function here that is this decreasing function. So there were various forms that were investigated, and these functions are decreasing functions of the covariance. And here the gain that you have between a certain initial step and the current time. So we had to use this approximation here, otherwise the rest remains the same, and dynamics, observations, assimilation actions are the same. And now there is some difficulty in choosing this heuristic function to check how much, to essentially evaluate what function would be best, essentially, to try to minimize, to find the optimal routes. So we did some very simple tests in which we had a very limited number of nodes, so that we could get an optimal results by brute force search, and we compared the optimal result to various functions, various decreasing function that could be used, and what was found in by the various functions. And we could vary also the parameters of these functions, obviously, to see the impact of that on the uncertainty reduction over time. So this was the analysis that we performed here. In terms of computational complexity, that's the key advantage of that is that now it's with this formulation, it's much faster than what we had before. So it's about 50 times faster in the simulation test, because we have this high reduction in the complexity related to the fact that we don't do this data assimilation step anymore. So it leads us to something that is tractable, and we can perform that analysis almost in real time for a certain watershed, for example, like in this Austin scenario, for this analysis. So it's something that is really helpful. I didn't also discuss the gains associated with the use of machine learning versus just shallow water equations, but also we have a huge gains there as well. So if we were using the classical shallow water equations for the estimation, that would lead to a much slower computation. So these are the algorithms that are used. So I'm not going to go too much into details here. That's just for reference. So this is so we start again with a certain state and with a certain prior and all, and then we search across all possible choices of actions, and at the end we find the optimal sequence of actions that minimize our objective with one or multiple sensors. So let's look now a little bit more at the results. So we made several scenarios with one or multiple UAVs, and to just try to see how we could reduce the uncertainty in the end in our state estimates. and what was the corresponding estimation error. So we tried the two approaches, and so the myopic approach is a one step ahead only approach, in which you just try to minimize the uncertainty at the next step, but without taking into account what would be the uncertainty after that in the future. So it's basically going to the next best location that you think will minimize the uncertainty when you will sense there. With the non-myopic approach, of course, you're going to use multiple time horizons. And then we did we gave some upper and lower bounds based on some Monte Carlo analysis where we randomly took actions. If you take random actions, you can get a sense of what are the best possible results in terms of minimizing the estimation errors or minimizing the uncertainty, and the worst case scenario also in terms of estimation or error or uncertainty. So you can see here that we are within these bounds that are obtained by Monte Carlo. This is not perfect, obviously, and so the blue curve, we'd like it to be as close as possible to this yellow curve, and here there is a significant gap. But the interesting part is that that shows also the interest of using a non-myopic approach. When you see that initially, particularly the estimation error or the reduction in uncertainty is not that great. So you still have quite a bit of uncertainty and quite a bit of error if you use just a one step ahead approach instead of using the entire information available. And of course, you don't have the perfect result that you would obtain with a brute force search. The optimal results, we are still far away from this optimal result, and that's the price to pay with this approximation of the information gain that is obtained through here this empirical function and that of the covariance matrix, and that doesn't require.
Sorry to interrupt, Christian. Sorry to interrupt. You have 5 minutes left.
Oh, sure. Okay, thanks. Thanks. Yeah. I think I'm very close anyway. So thanks.
Great.
So here, that would be. We still have to pay, as I said, this price, and this is related to the fact that we are using some approximation for the information gain. So we are not doing a full state estimation for across when solving the optimization problem. Okay, so here, this is now in terms of state estimate, how the estimates look like. So if you predict something, and so here, this is the prediction without any measurements, and this is with mobile measurements, and this is with randomly chosen measurements. So here, the less blue it is, the less error it is, and so the error is colored the error is shown as a shade of blue at different locations because it's a distributed value. So of course we want to be as light as possible to minimize our error. You can see that the prediction, so without any measurements, of course, in the system, you have quite a bit of error over time, and that comes from the fact that our prior is not well known, as well as the uncertainty in our model parameters. If you take randomly chosen actions for the robots, of course, you don't get something great either. At the end, you reduce the error because you keep getting measurements, but because you don't sense at the right locations, the reduction is not fantastic. With mobile measurements now, with this optimization, you can get something that is much better. That minimizes the error over some time horizon. We did also some analysis of the use of multiple UAVs with a group of fixed sensors. So if we have one mobile sensor together with a set of fixed sensors, what are the added information from the mobile sensors? And you can see here that this is the curve in blue. So when we add the mobile sensor versus having just fixed sensors, we get quite a bit less information error with even a single mobile sensor. So that really provides quite a bit of reduction in uncertainty. We also did some analysis of trajectories. So these are examples of two different trajectories with myopic and non-myopic sensors here that we can get. And again, the resulting decrease in uncertainty. And so with the non-myopic scheme, we have the least amount of uncertainty residual. And this is the state for reference. And we have also analyzed multiple mobile sensors. So if you put multiple mobile sensors, now you can also try to check. So here, without using this empirical function to represent the measurement of dates, you don't get some good estimation error. But with when you add this empirical function, that still reduces significantly. It's still not as good as, of course, as using what we should get normally, which is the optimal solution based on performing the data assimilation step. Okay, so now we'll just go very briefly to some other research activities. I have just, I think, very little time left. So we have done also quite a bit of work on variable speed limits, variable flow control as well recently. So that's some work for optimization of flows on highways with dynamic speed limit control, essentially. So this is something that is quite new, so I didn't want it to show that because we don't have full results on it yet. Robust control with turning ratio uncertainty, that's also something that we have investigated with second order count programming for performing robust control on highways based on the classical LWR traffic flow model. We have done also some work on autonomy, but that is more related to augmented reality-based guidance. So how can we use, for example, these smart glasses to guide users through intersections and to minimize the risk of collisions and to increase the throughput of intersections. So that's still a low-level control, but we have NSF CPS projects on this as well. And finally, just the conclusion. So what we introduced today is a path planning algorithm for mobile sensing in flash floods. The algorithm is based on the minimization of the residual uncertainty over some time horizon. And the main assumption of this is that we don't do assimilation at every step of the search. The uncertainty reduction is modeled through heuristics, so through some heuristic function. The future work is that we'll try to decentralize this path planning algorithm so that the computation can be performed in the nodes instead of having to do that in a central location. And we are also going to try to investigate higher dimensional systems. So here, this is fundamentally a 2D system, but we'd be interested also to extend that to the case of 3D system. For example, in the case of underwater vehicle, that would be monitoring a lake. In that case, if you want to get the concentration of pollutants, for example, that would be a three-dimensional system. So the paper, the associated paper, is on. It has been published recently on the Journal of Computer Science. It's the same title as this talk. So thanks everyone, and that concludes my presentation.